pleasure to be here. I want to thank Dan for inviting me to be a speaker in this series. I really treasure the opportunity. I've just looked at all the people who are online. There are so many familiar names. This is going to be fun to have a chance to speak with you in this kind of virtual way. And anyway, I hope you all are doing well, and I hope you're all healthy. It's been a tough year with the pandemic business, but we have done a good job locally with the vaccine. I've got my vaccine taken care of, so I feel pretty comfortable with this situation at this point. I hope you do too. Today's topic is benefits of using super absorbent polymers in concrete. This is arising out of a project that we have that is sponsored by Illinois Tollway. And so I'll be speaking a bit about some of the results we've had in the program, but as well, just some of the general background things as well. As we get started here, I want to make acknowledgements. First of all, introduce you all to the team that we have on this research project. Kamal Kayat, my very good friend and colleague from Missouri University of Science and Technology. Matt D'Ambrosia is also one of the PIs. Kamal and Matt and I are the PIs of this project. Matt is working with his MJ2 consulting company. And then I list some of the students and postdocs: Nima Farzania, Yunkun Gu, Kartik Padajay, Chuan Yu Shen, Rufi Zhou. Those are the students who have been primarily involved in the experimental work. And it would be a big mistake to overlook our big industrial supporters. I really appreciate the outreach of support from suppliers of SAP that have been involved here: Martin Matsushek, Scott Erickson, Mike Hensley, Steve Schaaf. And then a special emphasis on our contributions from Ozinga. Ozinga has helped us with field trials, and even field trials last year, but also field trials coming up. And Ryan Ciodella has been my most recent strong contact. And in doing so, you know who I left off? Theron. I didn't have your name on here, but you've been the contact that has drawn us close to Ozinga and helped us solve problems there. So Theron Tobolsky is one of our big supporters as well. And then a special acknowledgement to the Tollway. Dan Genkars is serving as our project manager on the Tollway side. I have the ACI logo up here too, mainly just to continue to give a shout out to the Illinois chapter, the international organization. ACI is doing very well. Maybe just that word of background. ACI made it through the pandemic year reasonably well. We have lots of programs going on internationally. And one of them is affecting Illinois chapter. And that is these research, the testing centers for the different testing that you do for, I don't know, the certification programs. So I'm glad that Illinois is going to be involved in that. And you will see that as kind of a trend moving forward, that ACI International wants to have strong support and presence, not only in the US, but around the world. And so we're working on that. We're expanding, always advancing, always advancing. All right, what is a super absorbent polymer? Let's start with the basic question. And almost always you get a quick introduction through baby diapers. It's something everybody can tune into. And the contents of the baby diapers that has that granular white powder is the magic stuff that makes them work so well. And that's a super absorbent polymer that comes, you can see in the middle picture. You can tell me if my cursor is not showing up. I believe it should be showing up. The powder in undry form is on the right. The same powder when wet is on the left. And you can see how much it swells, maybe 50, 100 times its original volume. On the left-hand, I wanted to mention the other uses. We see super absorbent polymers are not just created for concrete. Rather, they've been around for agricultural use, holding water down by the root system of plants and so forth, and They use them on golf courses, and they use them for waste retention and so on. On the right-hand side, you see two different kind of particles. If the superabsorbent polymer is basically created from a bulk material and crushed, we see particles that are very angular like this. And this, in fact, is how most of our products are, that they have this crushed, but you could get them in a beaded form. And we don't tend to see it that way in our product, in the materials for our work. Okay, the idea here with SAP is that we're going to add this material as a powder into the concrete truck and use its ability to hold on to water and then release it later on. There's sort of a competition for water, and the SAP particles will win that competition when there's an abundance of free water. And so they'll swell up in those first minutes of contact with our concrete. And then as the concrete mixes and goes through a setting process, these little beads or little locations of SAP, swollen SAP, will stay in the microstructure, reside in the microstructure until they lose the competition. That is, the hydration of the cement is going to kick in, is going to start fighting for water, and it will pull it away from the SAP when the time comes. And hopefully we've got the structure of the concrete all set and established, and that water is seen as like an extra reservoir to the paste as it goes through hydration. And thus it helps us overcome a phenomenon we call internal drying or autogenous shrinkage. And we'll talk a minute about that. So on this chart, we see the volume changes of concrete. And the one in red is shrinkage. We can have, of course, external drying shrinkage. That's why we cure routinely. But there's also this factor that comes in from the internal character of concrete. And there is the word chemical shrinkage. The shrinkage, you can't avoid this. This is part of hydration. That, and I'll see it on the next slide, that we encounter this chemical shrinkage, and it drives a certain kind of a desiccation of the internal microstructure unless we do some things about it. And of course, the whole idea of avoiding volume change is, let's see if we can get rid of the cracks. We'd like them not to be there. Let's see. So when we batch concrete, we distribute this on the right side, you see the mass fraction of the main components of concrete: water and coarse aggregate, fine aggregate, cement. And this is very familiar to us. We encounter every time we batch up concrete. It's normally done by weights. But we should take just a little bit of a moment to appreciate that the specific gravity, that is the density of these components, is not the same. So the volumes of these components will be different. Our coarse aggregate and fine aggregate have a specific gravity. Water has a lower specific gravity, and cement has a high specific gravity. So the volume, relative volume of the cement is down. And this little part here, the water and the cement, is the part that is chemically reacting during hydration. And this is the part that creates hydration products that undergo autogenous shrinkage. We're not going to get worried about any volume change in our discussion from aggregate, but we do from the cement side, the cement paste side. So external versus internal drying. So chemical shrinkage occurs with hydration. Autogenous shrinkage is measured on a bulk sample. And this is a very commonly used chart here, where you see originally at 0% hydration, we have just capillary water, the blue, and we have the cement, the red. And now as we move to 100% hydration, we have the hydration products and so forth, but we have something here at the top, voids. This goes through a 6% reduction, 6 to 7% less volume in the hydration products than the original water cement ratio, water cement volumes, okay? That reduction is called chemical shrinkage, and it's just part of the reality of our system. So if we were able to measure this with time, we would see autogenous shrinkage and chemical shrinkage. Autogenous is on the bulk sample. Chemical is just the definition of the materials themselves. And chemical shrinkage in red just goes up with hydration, keeps going up, 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 up. And then at some point, there's a departure. They basically are the same thing when the concrete is fresh and fluid and so forth. If there was any reduction of volume, the material just collapses on itself. And so here they are the same. Start of set, there's a departure. And now with set, the autogenous shrinkage is now going to start constraining and creating stress in the microstructure, because the free collapse of the material, because it's a fresh flowing material, can no longer occur. It's gone through set. So we have this deviation of chemical shrinkage and autogenous shrinkage. When that happens, boom, that is a time where stress begins. This is a time where that autogenous shrinkage starts creating an internal state of stress that causes cracking. And that's why we need to address this internal problem. This slide shows some micrographs of hydrated Portland cement. And you see this little micrograph here. And then the cartoon in the middle, when I hit the button, you're going to see a little animation of what happens. This, basically what we're thinking about is this water starts being consumed by hydration. And finally, I run out of free water and something has to give. What gives? And here comes the little water vapor bubbles. We'll call them bubbles. They're not necessarily bubbles, but these little zones are not thought of like a regular entrained air bubble or anything. They are little zones of water vapor where the liquid water is no longer there, but there's a pocket of water vapor, a pocket that has negative pressure. That is the stress is being exerted by the capillary forces on these little menisci. And the picture on the right shows that menisci, shows water, liquid water bound between these two surfaces, and then a meniscus, and then water vapor out here. That is a state of stress, or the origin of the state of stress. So if you want to know why would concrete start to crack itself, go through self-desiccation, this is the answer. That these little membranes of water start to feel stress across that membrane, and they exert stress on the solid structural framework of the microstructure. Okay, and then we can talk about the Kelvin-Laplace equation to quantify that in terms of the relative humidity out in this water vapor and the pressure that is being applied. So we want to try to stop that water loss if we can. How are we going to do it? Well, the basic idea is that we have, we certainly go through wet curing or conventional curing to keep water leaving from the external surface. But we also have this problem that would be true even if the material was perfectly sealed. This problem is not due to external drying shrinkage. And so we have this idea of internal shrinkage. And internal curing, the water, we need to find ways to put that water in a pocket and then release the water easily, but not too easily. If it's too easy, then we haven't even accomplished anything. The water is just free and moving around like it normally would. But we wanted to have some kind of a retention ability. So the water is held until a little bit later in the process. And you can see here where a couple percent drop of relative humidity creates a pull, a competition for the water that pulls the water back away from the superabsorbent polymer. Another common way to do internal curing is with lightweight aggregate. And so we've been comparing lightweight aggregate and superabsorbent polymers. The basic idea is the same. In case of lightweight aggregate, we have a porous stone, maybe 70% pores, and the water then sits in this saturated lightweight aggregate. And then when it is needed, it comes out fairly readily. It loses that battle pretty readily. The lightweight aggregate tends not to hold on to it very well, and it pulls away into the microstructure. And it's been, you know, relatively established as an internal curing technique. I think working with these lightweight aggregates is not everybody likes to try to source them and not tries to keep a stockpile of these. They're maybe a little bit hard to find in the marketplace. I don't know. But so there are reasons to think that lightweight aggregate is not necessarily a great solution for everybody. So super absorbent in polymers, here's a little description about how we measure the capacity of these things. We have an absorption behavior and a desorption behavior. And so if you wanted to test this, you might put a sample of the super absorbent polymer in a tea bag, literally a tea bag, like you make tea out of, with a paper around it to keep it isolated. And then as water is absorbed, the weight of the bag of saturated particles becomes heavy. We measure that. And then later on, we can see it desorb as there's some kind of a demand for that water outside. So in this case, we just saw some couple different samples of brands of SAP. And the simple point is not all SAPs are the same. Some absorb more, some absorb it more quickly. And so we would not want to make the mistake of saying they're all the same. Here is one of the reasons that they aren't the same: particle size. So we had different samples in our lab that we measured the particle size, and you can see that this is a fairly dramatic difference between the blue sample at up here and around a micron versus a millimeter. So down here around the under 100 microns, and so you can imagine that the amount of surface represented by these small particles would be greater. And so the reaction and the absorption rates of something small like that would be faster. Here's another point to keep in mind: distilled water and pore solution. Pore solution is not clear, plain distilled water. We know it has a high pH. In fact, that's why in concrete work, we have a lot of safety measures to keep it from, long contact with hands. You've probably experienced this yourself, where you have concrete on your hands and it feels like you really need to put some lotion on your hands at the end of that. So in the case of distilled water, just look at these numbers: peak absorptions, grams per gram. These are the numbers when you have plain distilled water and these 5 different SAPs, 100 times gram per gram of the SAP. Wow, that's a lot of absorption, right? And then we put in, instead of having distilled water, we use a pore solution, a solution with mimicking the high pH and the chemical constituency of the pore solution. And now look at those numbers: 16, 30, 25, 22, way low compared to the distilled water. That's a good thing to keep in mind. The behavior that we see in plain distilled water is not a good measure of what we need to expect in concrete. And furthermore, it's not even a very good predictor. The distilled water, look at this, goes 130 down to 16. Here, a sample goes 80 down to 35. They're just very different. So you might as well just ignore this kind of distilled water test altogether, because it doesn't relate to what we need to do. When we test our SAPs, we need to think about doing with this artificial pore solution test. A big question for new users is how much lightweight aggregate or SAP should be added to concrete to do the job. Okay, so the first thing we need to recognize is, what is our objective? We need to add internal water enough to offset chemical shrinkage. That's what we're going to try to do. And so we talked about what that chemical shrinkage is. We know it's 6 or 7% by volume of the cement. And that comes, in this case, I'm summarizing it as 7 pounds of water per 100 pounds of cement as a rule of thumb. In the case of lightweight aggregate, you want to make sure that you're using saturated lightweight aggregate. If it's dry, it's not helping you too much, or it doesn't seem, it won't work the problem as effectively as bringing it in as a saturated particle. In the case of SAP, however, we really don't want to bring that water in with the SAP in the already saturated SAP. This would be a globby mess, to be quite frank. So what we want to do is add it as a powder right when we're working with a mixing operation. So we can add it in, we've added it into the back of the truck. It actually goes in pretty well. Our testing shows it's quite homogeneously dispersed. So, you know, always wondered about that. Would this work to be dispersed in a truck if we, you know, did it that way right at the time of delivery of the concrete to the site? And our sense is that that's probably the best way to go, is to add it as an admixture into the truck right before using. And so when you do that, of course, you're going to get some effects. One effect is that you'll get slump loss. And we'll talk about that in a minute. Oh, I've lost my spot right there. So if we're doing this dosage calculations, this would be similar for SAP or lightweight aggregate. But we want to know the absorption and desorption characteristics of our material, and basically size the dose of the lightweight aggregate or superabsorbent polymer to give us delivery of that water. Dosing SAP. We know that SAP will reduce the slump. And so we somewhat have two choices to make here. We could add the SAP, suffer the slump loss, but then add in a superplasticizer to compensate. And that would allow us to have in our mind somewhat we're not going to change water. We're going to use the original mix design and count on superplasticizer to sort of do an offset of that workability factor. Secondly, B, we could add some extra water. And therefore, we would want to have a mix design that understood that. And because this mix design, we're going to change the water cement ratio if we do that. We would maybe avoid the use of the superplasticizer, et cetera. You know what? We early on all came to think that let's just do A. A is sort of the more reasonable approach, that we don't want to perturb the original mix design if we can help it. We'd like our strengths to come out as predicted by the mix design originally. And we also would like to think about kind of an easy approach to do this in the practice, that we have a lot of history with certain mix designs. We've used these mix designs. We know they deliver certain kind of properties, everything. It would be nice not to change all that. It would be nice to have the strengths come out the same, and the durability would, you know, kind of be maintained, and so on and so forth. And that's why A seems to be what we're leaning toward in terms of this. But it doesn't mean that you couldn't do this. So these would be all sort of developed by local trials to make sure you know how this material should be added effectively. All right. If we are able to add it, such as we saw with A, the method A, our water cement ratio is not going to be changed. We would hope that perhaps the strengths are going to be the same. Good news, in fact, all the testing seems to say that's true. We basically have sets of different kind of materials that we've tested, and the strengths are either the same or even maybe a little bit improved because of this more effective internal curing and the distribution. I guess I would say there's some argument about having a more homogeneous microstructure. But at any rate, we haven't been, there's not a reason to think that somehow the use of this SAP is going to create a spiral of problems with strength and so forth. We think that it'll be conservative, and that it will, your experience with strength should be just fine. But if you want to target a strength, I think we go back to cement mix design basics. We design for the strength based on a water content in the mix, the water cement ratio, and so on. Here's a picture, one of the SAPs. That's not colorized. That's the way the color the SAP was, a nice blue color. And so we've added it in there into the back of a truck. And in fact, it just blended. And one thing we notice is that it sometimes might get a little bit agglomerated on the surface of the blades, but I think that there may be even some ways to be clever about entering it so that it doesn't even have that much problem with the blades. So the main benefit that we're aiming for here is shrinkage, cracking, reduction. And these are some charts of the strains that we get from when we have autogenous shrinkage. And you see when we have 0 SAP, we have, in this case, 1,000 microstrains of drying shrinkage and autogenous shrinkage. These are sealed samples. But as we use SAP, we can offset that because as the system works to avoid this idea of desiccating the microstructure. Here's some samples that were wet cured for 7 days before 0. So this is a standard drying kind of an experiment where 0 is now a 7-day age, and we're drying samples. The control with no SAP is considerably more drying shrinkage than what we saw from any of the ones with SAP. That's our main benefit here coming through. We also have done some work with the restrained ring test. Actually, a lot of this work is still underway. This is a somewhat recent test where we cast concrete around a steel ring and then we put strain gauges on the inside of the steel. If you've not seen this test before, the first instinct is to be skeptical. You mean the concrete shrinking around the ring is going to be actually measurable on a big, thick piece of steel like that? The answer is yes. These strain gauges are real sensitive and they can pick up that squeezing action that the drying concrete places on the steel. It's amazing. And what that does then is it gives us a chance to measure that stress, and we can track that stress with time. In this case, that we get to about 6 days, and we keep building stress more and more and more and more and more, and then boom, something happens. What happens is called a crack. The sample, the ring of concrete breaks, all that stress is relieved, and we see it in the data. And so here's some examples with SAP. We have a plain sample and then 2 different SAPs. And here's the stress is building, building, building. And where the data ends is where it cracks. Okay, so it cracks at here about 24 hours. And these did crack, these SAPs did crack, but more at 35 hours and much lower stresses when that took place. So those are nice, vivid examples that SAP is making a difference. SAP improves durability too. So there's a lot of ways to think about durability. I just basically put in some data on lightweight aggregate, and there's some with SAP here as well. All together, the concept is, does internal curing really have payoff? And all the studies are showing predicted improvement in durability. So yes, they do have that payoff. SAP improves freeze thaw performance. Some people kind of speculate, yeah, aren't those little particles of SAP leaving voids inside the microstructure? Yes, they are. Well, the concept of air entrainment is to have a little void. It's a pressure relief valve and so forth. Does that maybe remove the need for air entraining admixture? No. So that's the finding. And the basic thing is the air void size from air entraining admixture and the SAP is much larger than air entraining admixture. So these are just some illustrative pictures, and I don't have data to sort of give a lot of size, but just take it as a truism that these voids from SAP are big and therefore have big spaces and therefore have limited ability to reduce freeze thaw stresses and degradation. So the data that I have here shows that our samples, we had some samples with no air entraining admixture, and then the same materials with air entraining admixture up here. Yes, the SAPs outperformed the reference with air entraining admixtures. So all of them were okay. All of them stayed above the threshold in the 666 tests. But when you don't have air entrainment, they all failed at some point before 300 days. And so they're better than having, the SAP is better than not having SAP, as you see here, but it's not good enough to say, oh, I'm just going to leave air entraining admixture out and assume that the SAP is going to work for me for freeze thaw. No, don't do that. So, but anyway, it's like, it's working in your favor. So that's a good thing. Other ways to control shrinkage. So before we kind of leave this topic, we want to certainly give a nod to other things that are done to control shrinkage. Shrinkage reducing admixture, these are just sort of like broad observations. I think that SRA admixtures are the real deal. They're finding a pretty good traction in the marketplace. And so I think people are finding them to be very useful admixtures, and they're the fairly new generation of admixtures. That's pretty exciting. Second, we could avoid all this self-desiccation, this chemical shrinkage problem if we were not so low. Part of our problem is self-imposed. We're always driving concrete strengths to be so high strengths and so very low water cement ratios. And so it's basically a problem that we beg for this problem. We're creating concrete that is known to have this demand for water that we are not providing in the mix design. We shortchange the mix with regard to water, and hence this whole subject. So you could kind of look for maybe opportunities not to be as aggressive. This is, I have certain themes that this is one, and the other theme I hit on a lot is that I think people trying to make concrete set and harden so fast, they don't realize all the downside to doing that and the penalties we pay when we overdo that. The speed of concrete set, the high strength of concrete, there are penalties that we pay. And that's, I guess it keeps us all in business, that we're all trying to solve these problems all the time and optimize a very complex system, multivariable system with lots of moving parts. The other thing is just good concrete technology. Use high aggregate content. Remember, this whole problem is in the paste. It's in that water and cement component of the mix design. That's where it all is. How can we squeeze the pie and get that to be smaller and smaller? Well, one way is to find ways to increase aggregate content. And there's another thing that we want concrete that flows. We want SCC. And these materials tend to have high paste content. And so it's like we're begging for a problem when we create some of these new materials that are really high paste, and it's going to have high shrinkage and so forth. So I guess recognize when you make these trade-offs, recognize what's happening. Don't stumble into these low water cement ratios and high paste content issues just because you're not paying attention. Okay, so that's my kind of brings me to concluding remarks. Our project has several months to go. We're excited to continue to work with the tollway. We hope to help development of guidance that will show up in tollway documents and specs and so forth. Broadly speaking, I am a pretty big optimist that these kind of things are like the internal curing, that the internal curing is going to find a lasting place in our industry, that it has a real payoff and real value that you can choose to take advantage of. I think that's one advantage I always kind of express to people I speak to in industry, that as you stay on top of these kind of next steps of technology, you're creating opportunity for your company to have higher quality, better performance, and perhaps a competitive advantage over your competitors who don't pay attention to these new advances. And that's why you want to be involved in ACI. And ACI is a community of people who are all about improving concrete quality. And it's a good neighborhood to be in. Be part of it. It hopefully comes right down to your bottom line. Thank you again for your attention. I guess I've completed the presentation and ready for questions.
Yeah, thanks, David. So it looks like we have one question so far in the chat box from Kevin asking if the bridge deck data that was shown, did any of those decks use SAPs or did they all use lightweight aggregate?
That chart had a smaller section at the top with SAPs and a bigger section underneath it with lightweight aggregate. Lightweight aggregate has a bit of a head start in this discussion of internal curing. Lightweight aggregate for internal curing has been a trending topic for maybe, I don't know, 20 years. And SAP is showing up in literature the last 10 years or so. And as a very broad remark, the people that are leading in SAP kind of research are also kind of originally got their feet wet in lightweight aggregate research. So this internal curing topic has certainly goes together. I treat it as a little bit of a continuous spectrum of solutions for internal curing. The concepts are the same. So I'd be interested in if people have a sense of how commonly lightweight aggregate is being used these days. Are people, finding that to be the satisfactory answer, or are you still in search of a silver bullet, a better way?
Yeah, I think a lot of people are still in search of that silver bullet. I know with my experience with the tollway, we've used lightweight aggregate for internal curing, also relied heavily on shrinkage reducing admixtures to address this very problem you're talking about. So having SAPs available, would give us another tool in the tool belt to address, the shrinkage concerns.
Yeah. Very good.
We did get another question in. Are SAPs incompatible with any typical admixtures?
They are very different than every other admixture I know. So in our kind of recent vintage of admixtures, we have the family of SRAs, the shrinkage reducing admixture. They're affecting the surface tension of the solution. Then we have things having to do with SCC. So we have a whole nother set of admixtures dealing with viscosity modifying admixtures, trying to gel the material to keep them from segregating when we have higher fluidity in the system. That's maybe a whole nother set of objectives. And then this SAP is a whole different animal. Here we're trying to absorb water, release water. It's not comparable to those other, newfangled admixtures.
So is it safe to say, David, that by adding SAPs, we don't see any unexpected reactions such as trouble in training air or anything out of the ordinary? I mean, you touched on the slump loss, but with a absorbent material like this, you would expect that.
Right. Yeah. I now that you asked that question, I realize I kind of was touched on these things kind of lightly. As a general rule, the basic behavior of concrete is not going to change very much by the presence of SAP. The water cement ratio is, everyone knows that's the big daddy. That's the one that changes the slump, changes segregation properties, changes set time even, and so forth. So as a rule, we did not see changes to set time. So even having this SAP in the microstructure didn't affect that too much. And then I mentioned strength, it didn't change that. So, and all the different strengths. So if you test flexural strength or compressive strength, or those are all kind of in the same family, and those are not highly affected unless you start changing water cement ratio. But we're kind of presuming that we can hold that constant. We'll work with the basic mix design. We'll suffer some loss of workability, but we'll add a super plasticizer to affect that. And so there's some tweaks to the kinetics, the setting behavior, but they're not dramatic. And they're going to be very manageable, I think, for people using this in practice. We even used a retarding admixture in one case. I mean, those things still work as you expect them to.
Okay, so there were a few more questions coming in here. Joni asked, does SAP affect the modulus of elasticity?
Yeah, I would put that in the category with the strength and the flexural strength, compressive strength, modulus, roughly the same. Those things are mechanical properties that will be more of a function of the aggregate you use, the aggregate pace ratios of how the microstructure is balanced out. So those, and our tests show that they are not changed much.
Okay, and there looks like there's a couple questions coming in on the restrained ring test. Vicky was asking why the SAP mixes would crack at a lower strain, especially since the cracking occurred at a later age. Yeah,
I noticed that too on that data. Vicky, I will speculate that some of that might be like a early creep behavior. You know, you're sustaining that stress for a longer period of time. It's not quite as high, but it's being sustained. And so it would work in favor of eventually driving cracking. And exactly how that works, I'm not sure. I mean, we don't have, that data was not from my lab, but that's, I guess it didn't surprise me to see that.
Okay, and it looks like
and Jeff, back then, wouldn't say that necessarily. I'd say that's an absolute rule that you'll see that every time. I mean, that's one problem with showing results from a single experiment. You know, maybe there's a reason that it's a bit of a unique finding.
Sure, and I think Thomas had a similar question, and I think he kind of touched on that.
You know, the issue with early age, we over time, we've done a lot of work on early age properties, early age shrinkage and so forth. And this early age shrinkage is a real interesting one. Let me tell you a favorite rule of thumb that anyone from my group probably knows this, but maybe not so much outside. When you have restraint of concrete that's cast into a project and it's got structural restraint, it might come from the base of a slab, it might come from contact with the structure, different kind of things. And perhaps you're worried about how shrinkage might create a state of stress. So you do some shrinkage prisms and you take a free prism and you get a prediction of what the concrete would shrink as a free specimen. And now the question is, okay, can I just use that to predict the state of stress in the larger scale project? And the answer is, if it's done from beginning, like constructed concrete project, the answer is cut it in half. The prediction is going to be about twice reality of what the real stresses will be because of the creep mechanism in that first week of time. That material is very young and very capable of creep relaxing the state of stress. And by taking about a 50% chop to that way of thinking about it as a function of free shrinkage, you actually do get real close to what we see in the lab in a careful experiment.
All right, Andreas had a question about the behavior of SAPs in ternary mixes. Do you have any experience or test results?
Well, I don't know that I have very much to say about the whole range of complex ternary mixes and using a lot of different mineral admixtures, limestone fillers or fly ashes or slags. And the reason I'm not expecting to see much is the argument about how it affects the microstructure is unchanged. Use any system you want. Tell me anything you want about the behavior of how much water is consumed and so forth. And if you have the basic original understanding of the chemical shrinkage, then the value of SAP should remain fundamentally unchanged. So I think it will be fine to use in any kind of system that hydrates with water.
Okay, I think that was all the questions I saw in the chat box. Oh, actually, another one just popped in. I think this is more of just a comment. I've been doing research on the SAP and other polymers as well. I work on powder admixture and using water-soluble bags to introduce the admixtures into the ready-mix concrete truck. I think it might be useful to use this SAP in the small powder form and mix with powder admixtures in the bag. As you know, SAP granules will agglomerate right away when it's in contact with water.
Well, that's okay. The timing thing is a real concern. The person asking the question is correct, that we have to be cognizant of the fact that there's a time here, the absorption time. Sometimes on the charts earlier on absorption, this action was happening within minutes. So imagine if you entered this material into fresh concrete and left everything unmoving, just sitting there. It would have a somewhat of a problematic gelling, and you need to think about distribution. So if if you're using a truck mixer, there's going to be a natural dispersion of this. And we wondered about this too, whether the effectiveness of a truck mixer would really get the homogeneity that we want. And right at this time, I mean, we're confident it does. So we think the truck mixer is a good example of enough energy in the mixing to get us to a good dispersed result. But you're right to be concerned about it. And so even if you're doing things in the lab, you need to think about that too. How can I get a really good quality dispersion of these particles that are simultaneously swelling and absorbing water?
Hi, Dan, David. I'm sorry to interrupt. I'm not the presenter, but I raised that, like information is because I am working on the powder, or we are selling the powder. My company is using the powder, and we mix that kind of SAP. Well, of course, I'm not just only working on the SAP, but also with other kind of chemicals that behave similarly. I cannot tell you what kind of polymer it is, but like since your presentation is on the SAP, that's what I just give a clue. That's a benefit of using the powder admixtures and then mix it properly so that the particle is further away to each other. So whenever it's introduced into the concrete, it's distributed uniformly. So
Yeah.
there will be no jelly. And
That's
I introduce it using the water-soluble bag. Well, mix the powder admixtures and SAP or other polymer, and then mix all together so that the particle is further away from each other. So whenever we introduce into the concrete, there will be no gelling. It will gel in the particles, small particles. So that's the way I introduce it. That's why this is a benefit of using the powder admixtures in this case.
Yeah, thank you, Darmo. That's a nice remark to reinforce the idea.
Yes.
You know, it's kind of interesting that most of our admixtures we use today, like air and training admixture or a super plasticizer, we use in liquid form. And
Yes.
I think the reason we do that is because it's easy to automate and dose in practice.
It is true.
And but you know, when we were doing our first experiments with super plasticizer in the late 80s, we used powdered. There was a kind of a standard super plasticizer from Japan called Mighty. It was a standard everyone used for a while, and it came as a powder. And it was, the beautiful thing about that is if you're doing laboratory work, you know how much you're weighing very carefully,
right.
and you can control the water. If you're taking commercial SAPs, who knows exactly how much water is in there? I know there's a volume, and it's not very much the active molecule of the super plasticizer. It's a lot of water in there. How much water is it? And do we count that as part of mixed water? You know, a lot of questions. So at any rate, we are, the world of working with concrete research is sort of straddling a line. In one foot, we try to be careful chemists. That is, use a powder that you can measure with great precision and you know how much water is not there, you know, zero water in the powder. Or use the commercial admixtures because those are what's being used. So it's done both ways. Clearly the research community needs to speak to practice as well. So we use a lot of commercially prepared products like super plasticizers.
Yeah, again, you are right. I'm happy that, I catch, that you give excellent presentation like this, and it's really related to my company and my work, so, and this is excellent, really excellent. I thank to David and also to Dan and to the ACI in Illinois, so. But there is a benefit of using the powder admixtures, and also right now it's very common, as you said, using the liquid admixtures. That's true, but there are some plus and there are some minus using the powder admixtures. One of the plus is that's the way how to distribute very fine SAP, for example, into the concrete. And later on, whenever it's the concrete getting hard, that particle size is very small.
Yeah.
And it's not gelling. That's the point. Thank you again.
Yeah, I think those were great comments. And I think this has been a great presentation and a good Q&A session. We are running short on time here. So I'd like to thank David again. We really appreciate you taking the time to share the benefits of using super absorbent polymers in concrete. And thanks everyone for attending. Keep an eye out for our monthly newsletter or check out our website anytime to get the latest information on the chapter. Just a reminder, we have our last virtual meeting of the season, May 20th. Topic will be low compressive strength test results. Sign up link is already on the website and it will be included with the May newsletter. So thanks again, everyone, for attending.
Bye.